So last time I actually managed to get to proving the free will theorem, which, remember, says that spin, twin, and min, which is roughly approximately equal to fin, that's the finiteness of the speed of light, plus free will, plus, let me say, human free will. I'll just abbreviate that to FW, that together, they imply what I call particle free will. The definition of free will in both cases meaning that the behavior is not determined by the past, is not a function of the past. And I suspect that most physicists feel, first of all, that that's a tendentious way of putting things, and that one shouldn't really do that. One should be a bit more conservative. And second, that they already knew it. Because for a very long time now, it's been sort of known that quantum mechanics had this property that it wouldn't predict exactly what was going to happen. That's since the 1920s. And since the 1960s, that's been made a bit more precise. And you have other statements. A stronger statement is that quantum mechanics, or any theory extending quantum mechanics, has this sort of defect, if you like to say it that. So I want to point out that this theorem really is new. And one way of doing that is by showing you some of the scientific consequences of it. But let me sort of explain. We don't suppose in our theorem quantum mechanics. These two are two testable, I would write operationally definable consequences of QM. Testable consequences. You don't have to believe all of QM. Not only are they testable consequences, but they're sort of, in principle, quite simple. You can understand them without understanding QM. You can understand what they assert. And that's one thing. So the physicists aren't usually concerned with logical implications. They're concerned with the facts. That's very proper of them. I mean, it's a natural thing to be. But mathematicians are concerned with the nature of the implication. And what I'm saying, what I've just said, is this doesn't suppose as much as the previous arguments in this direction. And the conclusion is really stronger. It doesn't say just that some theory or other, or some type of theory, will not predict what the particle will do. It basically says, the particle doesn't know what to do yet until you do the experiment. It can have two different consequences. So that's going to become clearer and clearer, I hope. Okay, where are we? Environment, image on. And, what have we got? Okay, we've got, I've got to take this back to slideshow now, view. Help me. I should have noticed that it wasn't on the... Where are we? It say OK or cancel or something. No, I want to view it normal. View normal, I think. Okay.
John, please.
Okay. Okay. So where are we? Let me see. Okay. Here we are. Well, first of all, so what I'm going to concentrate today is the sort of scientific consequences of this free will theorem. Some of them are things that have been known for a long time, but we're proving them in that case from rather less than has usually been the case. Some of them haven't been known. Well, first of all, I'm going to take two statements made by people who are known as philosophers more than scientists nowadays, but these are really scientific observations. Descartes had this principle, this dualistic attitude. He said, well, here you can see his words, the will is by its nature so free that it can never be constrained. That's asserting the existence of human free will. He regarded it as a property of the mind or the human spirit. And on the other hand, determinism, he even thought that the rest of our bodies, if you cut off the mind somehow, the rest of our bodies were robots. I didn't bother to say that, but I mean, in particular, everything outside minds was robotic according to Descartes' physics. So in particular, the world outside us is deterministic, and that you can't have. If we humans have free will, which Descartes does explicitly say, then so do the particles, even particles outside us. So that disproves this possible duality. I don't know if anybody took it seriously after 1940 or something, but maybe they did. And here's Leibniz's principle of sufficient reason, which he enunciates several times. This is one of the clearest, that nothing happens without a reason why it should be so rather than otherwise. I think he rather applied it to human free will too, but let's apply it to particles. A particle can do one thing or another. There's nothing in the past history of the universe that tells the particle what to do, says the free will theorem. So if it can do A or B, why does it do A? What's the reason? What's Leibniz's necessary reason that it should give A rather than B? So there are two sort of good old-fashioned statements disproved, but they're scientific statements. Right, now I'm going to introduce this principle here. Sorry, I'm just thinking what to say. I'm going to introduce a little sort of model for physics, which I'm going to call the hexagonal universe. And it's a very simple model, so don't be scared of it. Space on this principle, in this physics, is one-dimensional. So space-time, oh yes, let's indicate space going this way and time going this way. Okay, and there are some inhabitants here. Okay, so I think of this as day zero, and we have two observers in this little world. Okay, and they both start on day zero here. And, well, we can have several observers, it doesn't matter what we have. But the rules of the physics say if you're at a given place on day t, then you're in one of these two places. These are the only possible moves to day t plus 1. And this is a sort of analogue of the Finn axiom, because it ensures that you can't travel. Travelling means going to left or right. You can't travel faster than a certain speed. You could either travel left as fast as you can, whoops, or right as fast as you can, but on day t you'll only be at most t steps apart. It's also possible that you just sort of zigzag in some sense, you know. Okay, so that is the analogue of Finn. Now, I'm going to have now an analogue of the which is it? The spin axiom. So can I just say an analogue of Finn? In this universe, people can't travel very fast to the left or right. And of the spin axiom, it says, oh yes, let's say there's a number, I'm not quite sure where to write it. Let's say each hexagon conceals naught or one, and until you get there. I mean, right, what am I going to say now? When you get there, am I going to be, yes, okay, there's my hexagonal universe again. Whoops. When you get there, three hexagons like this have 0 or 2 ones. Okay? So if this is a 1, then one of these must be a 1. Exactly 1. Let's say that. But you can't tell which it is until you actually get there. That's rather like the spin axiom that said, you know, of a particle, that if you ask it 3 orthogonal questions, you get 2 ones and a 0. Okay. Now, it's rather peculiar. Oh yes, so the question, I'm going to introduce this wonderful concept of Janus. Now, Janus, you may remember, was the two-faced god of Roman times. His image appeared above a doorway with one face looking in and the other face looking out. By the way, we get the name of January from that, because January could be near the beginning of the year, could also be regarded as ending the previous year. Okay. So, first of all, I want to sort of show you that these axioms, the analogues of spin, twin, wait a moment. Yeah. Well, I haven't really got one for twin, but in a way it's there because the actions, remote places are related. let me sort of demonstrate what happens. If, okay, well, you've got this in front of you at the moment. Suppose that this, I've got 4 hexagons, I think, here. I'm not sure. No, 5. Oh, whoops. North 1, 1, north 1. Suppose they've already seen this. This happens at day 4. I'm going to show you how Janus, who's the operator of this universe, how Janus can arrange that these conditions are true. What happens is, even Janus hasn't worked out what he's going to put here. Until one of the 2 experimenters gets here and effectively asks a question, does an experiment. Okay, and then Janus tells the answer. I'm going to suppose here that the right-hand player gets there first, or got there first, and I'm Janus. Okay, this arrives at 0. Now, Janus instantly works out 0 and 1, that forces a 1. 1 and 0 forces a 0. 1 and 0 forces... 1 and 0 forces a 1, sorry. 1 and 1 forces a 0. 1 and 0 forces a 1. Have I got this right? 0 and 1 forces a 1. So I worked it out this way. Okay. But you'll notice I've got the same answer, if I got it right, as this way. Janus used his right face just now in front of you to work out this, but he could have used his left face. And looking at the way he did it, there's no way of deciding which way around Janus worked. That's a big deal. This law of physics is left-right symmetric. Notice I said how Janus might work, but I've demonstrated that we would have achieved the same result if he did it the other way. Well, I can't manage to mimic in this little universe the relativistic thing that the time order of events depends on the position from which you watch them, or the coordinate frame that you use to watch them. But it doesn't matter here. We could treat this one experiment as having been performed first, and then in that case we'd work it out the way it is on the slide, or we could treat this one and you get precisely the same effect. Okay, well, try and bear that in mind for a moment. Okay, so as you see, maybe Janus did work from right to left, but the inhabitants of this universe can't actually tell which way Janus worked. It's sort of meaningless. And the point is, the physics that I just described here, very simple laws of physics, 2 1s and a 0 or 3 zeros, the physics is left-right symmetric. But this Janus model that we've invented doesn't respect that symmetry. And what that really means is it can't be the explanation for the model. Now, there's a sort of funny thing here. You see, our players, our inhabitants of the universe, can move only at a bounded speed. But Janus can fill in the physics. Janus threw a coin somewhere and immediately followed the consequences of it. So in a sense, Janus can move faster than the speed of light. move faster at any speed you like. But, the person who operates the model isn't in the model. And this is really quite an important thing that mathematicians are very used to. We are used to creating models for set theory, and what's true inside the model is not the same as what's true outside the model. I was very, very surprised by this a long time ago when I was trying to prove that the axiom of choice couldn't be proved inside set theory. And I looked at Mostovsky's proof of a rather weaker form of this statement, and he supposes the axiom of choice right in the first line of his paper. And I thought, he's trying to prove that the axiom of choice can't be proved. Why is he supposing the axiom of choice? It seemed ridiculous to me. But it's perfectly sound principle. Using the axiom of choice, he produces a model in which the axiom of choice is false. We're not used to constructing models for the universe in the same way. We don't sort of customarily imagine ourselves stepping out of the universe. It seems a rather godlike thing to do, impious maybe, to do that. But it's a perfectly valid method of argument. So let me say what this Janus model for hexagonal physics does. It proves that you can't get any contradiction from these axioms. That's not perhaps too surprising, but let me move on to a case where it's perhaps a little bit more surprising. Okay. Perhaps I should say this is a thing known perhaps more among philosophers than physicists or scientists, but Curie's principle is this principle, technical term, for a theory that doesn't have the symmetry of the facts it's supposed to explain. Let me talk about solipsism for a moment. Solipsism is associated with the name of Bishop Berkeley, as we say it in England, and as he actually said it, although the university named after him is called Berkeley. But anyway, it's perhaps unfair to attribute this to Bishop Berkeley because he had more subtle ideas. But let's take solipsism in its nice, simple form. It's the theory that I'm the only person in the universe and that you're all figments of my imagination. And it's cheap, really. I mean, you can't disprove that. All you can say is, well, to Conway, I mean, maybe I'm just a figment of your imagination. Well, that's really what's wrong with solipsism. Solipsism doesn't respect the symmetry between people. Okay? If I say I'm the only person in the universe, the only real person, and you're just images on my retina, and so on, well, you can make the corresponding assertion backwards. So the facts that face us have a certain symmetry we observe. It's perhaps not all that obvious that they have a symmetry. I still think that I'm pretty important. But, they do appear to have a symmetry. I don't say that too publicly, that, that I'm special, but, well, there we are. And anyway, what was I going to say? Now, a non-relativistic physical theory is really a kind of Janus model, because physics has been verified to be relativistically invariant to a very, very great extent. All sorts of experiments have been performed. And if you have an explanation that isn't invariant, it cannot be the explanation. Perhaps let me say why it cannot be the explanation. You take a symmetry that it doesn't obey. By definition, if it's not relativistically invariant, there's a relativistic transformation that takes it into a different explanation, not the same explanation. And there you have two competing explanations. It's rather like the two competing explanations in solipsism. I'm the only person in the universe? No, I'm the only person in the universe. It's just as good a theory. Well, perhaps I can't say that about my theory and your theory, but I can say it about your theory and your theory, you know. They seem to be equivalent from my point of view. And if one of them were an explanation, the other one would be an explanation that's just as good. Okay, so how do we prove that the real axioms spin, twin, and fin are consistent? Well, I build a model universe. I don't have to get every detail of the universe right. I'm only concerned in getting these particle experiments right, these twinned particle experiments. So Janus selects an arbitrary frame of reference. So that means he's got a particular time order that especially interests him, you know. And then, when one of these experimenters, big A and big B, asks a question about his particle, interrogates his particle, Janus responds. Now, take the first of the two questions about our little twinned particles A and B that happens, the first one to happen in Janus's time notion. Okay? Janus takes out a coin and throws it and determines the answer 0 or 1 by the throw of the coin. That certainly means that the experimenter can't tell what it's going to be before the experiment. That's an important sort of thing. What now happens if the other experimenter asks about the other particle, asks the same question? Well, Janus takes care to give the same answer this time. He doesn't throw the coin again. What happens if the first experimenter asks a question which was at right angles to, a question in the direction at right angles to the direction of the first question? Well, Janus, if the first answer was 0, Janus answers 1 because he's got to. If the answer was 1, he answers 0 or 1 at random, say. It doesn't very much matter. He just takes care to obey these two axioms, spin and twin. If he does that, then as far as the experimenters are concerned, he's making the universe behave the way our universe apparently does. I'm not telling Janus what to do about all sorts of other problems. I'm not attempting seriously to simulate the whole universe. And now, I want to say that Janus doesn't have to obey Finn. If the second experimenter asks a question arbitrarily soon after the first experimenter, despite the fact that one of them's on Earth and the other one's on Mars, so light can't travel, well, Janus can fill in the answer. Janus is not bound by the rules that the experimenters are bound for. He's not bound by the rules of the universe himself. He's the operator of the universe. He's a kind of God. But Finn can hold for the experimenters. There's no doubt about that. Okay, so what's wrong with this Janus model? I use this term Janus model as a sort of insult. It's a perfectly reasonable explanation. The world could be operated like that, okay? But it's not symmetric. And the facts are symmetric. It doesn't obey Curie's principle. So no one of them is the true explanation. If Janus, the results that could be obtained by one Janus, or should we say one face of Janus, using one particular time ordering of events, the universe it simulates are precisely the same. as the facts that obtain in it are precisely the same as the facts that obtain in another universe, controlled by a different face of Janus. So these are not explanations you believe in. Okay, you should believe in at all. Like solipsism, they're too cheap, really. But the technical defect is that they don't satisfy Curie's principle. But they do serve an important thing. If you felt, and many people do, that thin and twin contradict each other, they sort of go against each other, how on earth can these two particles' behaviors be correlated when they can't transmit information to each other? You might have thought they had to transmit information to each other somehow. But they don't, because thin holds in this kind of universe, and so does twin. So they don't actually contradict each other. That's quite a big deal for a logically minded mathematician. You can't deduce any contradiction. So you might feel uneasy. You might feel, oh, I don't know what's going on. Well, I don't know what's going on either, but it could go on. But the only proof I have that it could go on is by a non-relativistically invariant construction. So it's not the explanation. It's not the explanation. If it's an explanation, then there's another one. Okay. So now I have to talk about hidden variable theories and what's wrong with them. The sort of standard way out that's been proposed many times is that there's something inside a particle, say, that effectively tells it what to do. A hidden variable. We can't see it, and that's the only reason we don't know what it's going to do. It's hidden from us, but it's not hidden from the particle. David Bohm invented this phrase, hidden variable, which he used in his theory on his book on atomic physics. Later on, he espoused the hidden variable theory himself, which seems very strange. But what the free will theorem says is that no hidden variable theory can be both relativistic and deterministic. I should have said and true. I was sort of restricting myself to true hidden variable theories. You can have a hidden variable theory that does anything. But the reason, well, if those hidden variables are there telling the particle what to do, they are essentially in its past already, and so the past tells it what to do. What it does is a function of the past. But the free will theorem says, no, the behavior of the particle is not a function of its past, provided the same property is true of us. And now comes a really surprising observation that I think Simon and I are the first people to make. So you see, there's a certain confusion in people's mind between, how can I say it, between non-deterministic and random, or at least partially random. People think that if a theory isn't deterministic, it must be because God's playing dice with the universe, in Einstein's famous phrase. Einstein obviously thought that. He said, you know, I cannot believe that God plays dice with the universe. And he said that in answer to Bohr's observation that quantum mechanics wasn't predictive. So he was using it as an argument against quantum mechanics. Okay. I like playing backgammon. The only thing you need to know about backgammon is that it's a game that involves dice. And now I'm going to tell you what happens in backgammon tournaments, at least in many backgammon tournaments. You have, say, 50 tables, and at each table there's a couple of people waiting to play. And normally, when you play backgammon just against an opponent, you throw the dice. Then that determines who starts. It also determines something about what their move is. It also restricts their first move, and so on. But in a backgammon tournament, quite often, the tournament director says the first throw is a 5 and a 3. And then the person to start at each table must make a move that's legal if 5 and 3 are thrown. But of course they make different moves because they have different ideas about what's a good move for 5 and 3. And then the tournament director says the next throw is double 6, and so on. That doesn't affect the play at any table. It's a device to make sure that there's nothing about the throw of the dice that's treating the players unfairly. Each table receives the same throw of the dice. Okay. Well, that's an analogy. Suppose that what a particle does is influenced by its past, is determined by its past and some random numbers. It's as if God throws the dice in Einstein's metaphor and says the first throw or the current throw is a 5 and a 3 or something. And then every particle in the universe instantly hears this 5 and 3, this deep-voiced 5 and 3. That doesn't help, because rather than throwing the dice as needed, one could imagine that they were thrown beforehand. That, in fact, there's a big table of random numbers, and God's just reading that off. Or the particles can perhaps read it straight off without needing a God. But in any case, it doesn't affect the validity of any potential explanation of the universe. Okay? But now, all throws are in the past. Okay? And so the particle's behavior is determined by its past. And the past includes all those random numbers. On the other hand, that contradicts the free will theorem. Okay? So somehow we have managed to produce a situation where, it's conceivable that God does not play dice with the universe. If the free will theorem is true, God does not play dice with the universe. The opposite of determinism isn't randomness. It's a new property, freedom or something, which cannot be explained in terms of randomness. This is particularly interesting, I think, to philosophers who are trying to relate free will to moral judgment or something. I mean, am I morally responsible for my actions? And if the world is deterministic, it's difficult to maintain that I am. The world is deterministic, including me. So I'm going to plead to a judge, that no, I did murder the man, but I can hardly be held guilty because I was forced to. Some philosophers have said, well, okay, suppose you do have free will. I mean, suppose the world isn't deterministic in that sense, then isn't that really rather like having a sort of tick? I'm jerked in some way. I'm influenced by something random. There's nothing different about that. So it still doesn't solve this philosophical problem about moral responsibility. Well, I'm not pretending to solve that problem either, but I'm pointing out that the opposite of determinism isn't randomness. Random things, well, let me proceed to the next thing. How does free differ from random? Well, we don't know how to define either of them, but they're different. And the way we know they're different is that random choices can be made in advance, okay, and it doesn't affect the theory. But free choices can't. And the reason, well, I've put in brackets down there, the Cauchy-Specker paradox shows that B's response can't precede A's choice. Okay, now something a bit more technical. In the usual sort of picture of quantum mechanics, it's supposed that there's a thing called the state, and the state, well, let's say the state of a particle is rather like, it's a predictor of the probability that it's in a given place at a given time. And so the state is like a series of concentric circles in a certain sense when you drop a stone into a pond. And the state evolves in a continuous way. Technical term is the unitary development. But then, every now and then, and particularly when you make a measurement of the particle, you don't find it smeared out, you find it's a particular spot. And then from then on, it will expand again. Well, sorry, this is only a picture, not a terribly good picture of what might happen. We alternate this continuous unitary development during which time the particle, if we're talking about a particle, is smeared out in some sense. At least what we know about it is smeared out. And that alternates with collapse of the wave function. This is a collapse of the wave function. Okay. Well, what our theorem implies is that there can be no perhaps I should say, this behavior is not only continuous, but it's sort of predictable. Exactly. But when you do this collapse, in particular when the particle hits the screen is probably a collapse, you can know the collapse is going to take place, but you don't know, there's no way of predicting where the particle's going to be. In other words, which particular collapse may be, why didn't it finish up here? Well, our theorem implies that there is no mechanistic explanation of collapse. It's only if we suppose the various things we've supposed, the Finn, twin, spin, axioms, and so on. And why can't there be a mechanistic explanation? What I mean is something that explains why it goes to where it goes. Well, if in particular it would explain where it goes, but that's the only non-predictivity in the system, and it's got to be non-predictive in the end. People have proposed mechanisms for collapse. Let me continue with the sort of general thing here. We suppose, really, but it's buried in the min axiom, we suppose human free will. And I'm going to give arguments next time that support the conclusion that we have free will very, very strongly. But nonetheless, it sort of can be thought of as a defect of our theorem that it uses free will. Free will is a somewhat nebulous concept. nobody feels happy, no physicist, I think, feels happy with the notion of free will. But it's become customary ever since Newton to demand of a physical theory that it can work in essentially arbitrary initial conditions, and not to demand an explanation of the initial conditions. Newton differed in that way from Kepler. Kepler gave a number of reasons as to why the planets were at the spacing they were, and so on. We don't bother to explain that nowadays. That's just the given condition. They could have been essentially at any spacing. Your theory, and Newton's theory had this property, predicted what happened from arbitrary initial conditions. And that's a substitute. The only way in which we used free will, human free will, is in the experiment to select whatever experiment they wanted to perform. If we say that your theory has got to give answers, whatever the initial conditions are, then you can remove the need for somebody to select them. So that means that the free state assumption, the free initial state, eliminates the free will assumption. So if you don't like free will as a hypothesis, you can sort of say, well, we can say what we say here, that deterministic free state theories can't explain the behavior of particles. Now there's something which is still popular, well, it still happens all the time in popular accounts of physics, and I'm sort of calling it a New Age effect. And it is that the spin of a particle is influenced by the observer or something. It's got different formulations in a way. Even Eugene Wigner believed this at one stage, although he disavowed it later. He thought that reduction was performed by a conscious mind. It happened when a conscious mind observed the thing. He disavowed it later, and it is a bit strange. Penrose points out there are discussions of cosmology in which one explains the formation of the galaxies and the mass distribution in galaxies and so on by supposing they were quantum fluctuations in the very, very early history of the universe, shortly after the Big Bang. But then it's really rather difficult to believe that when Edwin Hubble noticed these galaxies, or actually people before him noticed them, that, he reduced them. That they weren't anywhere, they were in a smeared out state until somebody actually saw them. And actually, come to think of it, one should go back to Herschel rather than Hubble, but anyway. And now it's easy to sort of fall into this. So we've proved that the spin of a particle, I really mean the squared component of spin in a given direction, does not exist before its measurement. Oh my. It's the same wretched person who's telephoning me. And they're telling me that the warranty on my vehicle, this is the second warning that the warranty on my vehicle, well, they say it's the second warning, it's the 22nd warning at least, and I don't own a vehicle. But anyway, so yes, we proved that this spin, and I added a few words to that, of a particle does not exist before its measurement. It cannot exist because a consistent set of answers, a set of answers that's consistent with the 101 rule, which is a law of physics, doesn't exist. So that's the basic reason it's impossible to suppose what the answers are, because the answers would disobey this physical law. But if instead of before its measurement, you say before an observer measures it, doesn't sound very different, does it? And then if instead of before an observer measurement you say it depends on the observer, and then you say it's influenced by the observer, these are gradual changes. And then in the end you get the new age view that reduction needs a conscious mind. Well, you might have gathered from the sarcasm that I used that I don't actually believe that. There's no evidence that I know of that a conscious mind is needed for reduction. Yes. Where are we? Okay. I'm thinking of giving up now. That's reasonable because, let me say, I was discussing today the scientific consequences of the theorem, and they do exist. They're non-trivial. And moreover, they don't follow, all of them, from what the physicists knew. The physicists already knew, I'll put "knew" in quotes, that you can't predict what particles can do. That's old hat, very old hat. Our theorem is stronger than that in two ways. It supposes less, and it proves more. It proves not just that quantum mechanics won't predict what they do, or any extension of quantum mechanics, but that they really don't know themselves what they're going to do, in a certain sense. But if you don't like that anthropomorphic way of speaking, their behavior is not determined by the past. So given the entire past, there can be two different things that the particle does. Okay. Well, next time what I'm going to do, it's rather strange. Free will, we supposed free will. I've supposed it all along. I minimized its use in the axiom min. But the axiom min contains the assertion that the experimenter is free to press one of 33 buttons or one of 40 buttons, whatever it is. He's got a certain amount of free will, non-trivial amount of free will. And then we proved that the particle has even less free will, but it has a bit of free will, namely, it can choose to give the answer 0 or 1. Oh no, even that isn't quite so. Two particles together can choose to give 0 or 1. So it has not just one bit of free will, one bit of choice, but half a bit, really. Okay. So how can it be that if we've supposed human free will, we can end up, as I shall next time, producing a whole lot of very strong arguments in favor of free will? Well, the answer to that question is they are not deductively valid arguments. They're not using deduction. But, in court, you don't prove the prisoner guilty by purely logical deduction. You appeal to common sense, really. And that's what I'll be doing next week. I'm hesitating to say something about it. No, I don't think I will. I think it's a good idea to stop now. Let me remind you that we know we cannot use deductive arguments to prove it. I'll go over the argument just now to recall it to you, or for those who weren't here. Suppose we are, I call it the second time around argument. Suppose that we're in the universe playing again, so to speak, for the second time. Then we're being fed exactly, this is the supposition, we're being fed exactly the same sense impressions as we were first time around, which might be 100 billion years ago, before the second time started. So even if the first time around was non-deterministic, had free will all over it, second time around everything is exactly the same as it was the first time around by supposition. And we don't have free will anymore. What we do is determined by the past. You might feel that that's a somewhat extravagant supposition, that there can be a second time around. Okay, but I don't have to prove that there can be. If you want to maintain that determinism is impossible, you have to prove, the onus is on you, you have to prove that we cannot be in the second time around. Okay? And you'll find that hard to do because everything's the same by supposition as the first time around. So we know we cannot prove that we have free will by deductive means, by absolutely sound means. But that doesn't stop us making it very, very likely indeed. I'm going to give up. Okay. Mm-hmm.